Today is February 2nd, 2026. If you are new to the channel, welcome. 4 days ago, Earth did something it's only done once before in recorded history. And what happened in those 24 hours has seismologists around the world questioning everything they thought they knew about how our planet works. 15 earthquakes, all magnitude 5.0 or higher, scattered across the globe within a single day. Chile, Japan, Indonesia, Iran, Fiji, not clustered around a single fault line, not following any predictable pattern, just everywhere. But here's what's keeping scientists awake at night. Not a single one of those quakes exceeded magnitude 6.0. The energy didn't concentrate, it distributed, like someone took the planet and squeezed it from every direction at once. And it happened exactly 16 days after the strongest solar radiation storm in 2 decades. On the exact day Neptune entered Aries for the first time in 165 years. Welcome back. Before we dive into what this means and why the timing of these events is making even skeptical scientists reconsider everything, make sure you're subscribed and have notifications turned on, because what I'm about to show you connects dots that most people aren't even aware exist. Let's start with what we know for certain. January 26th, 2026 started like any other day. People went to work, kids went to school, the sun rose over a planet that seemed perfectly normal, but beneath the surface, something extraordinary was happening. Within a 24-hour window, seismographs around the world registered 15 separate earthquakes, all measuring magnitude 5.0 or greater. Now, if you're not familiar with earthquake science, let me put this in perspective. On an average day, Earth experiences maybe 1 or 2 magnitude 5.0 quakes, sometimes none. The planet is constantly moving, constantly adjusting, but major seismic events are relatively rare. That's normal. That's baseline. January 26th had 15. But the number isn't even the strangest part. It's where they happened. Look at this map. Chile, Japan, Indonesia, Papua New Guinea, the Philippines, Iran, Fiji, New Zealand. These aren't neighboring regions. These aren't connected fault systems. Some of these locations are on opposite sides of the planet. The Ring of Fire lit up? Yes. That's expected. That's where most earthquakes happen. But so did parts of Central Asia. So did regions that don't usually sync up with Pacific seismic activity. Seismologists call this a synchronized release, and it almost never happens. Here's how earthquakes normally work. A major fault ruptures somewhere, usually hitting magnitude 6.0 or higher. The ground tears, buildings fall, then come the aftershocks, smaller tremors radiating from the rupture zone like ripples in water. It's violent, yes, but it's localized. It makes sense. One fault breaks. The stress around it adjusts. The Earth settles back into its uneasy equilibrium. But January 26th didn't follow that script. There was no main event, no epicenter, no aftershock sequence. Just 15 medium-sized quakes firing off in different hemispheres within hours of each other. None of them exceeding magnitude 6.0. The energy didn't concentrate, it distributed. Let me put the energy release in perspective. The total seismic energy released that day was roughly equivalent to 2.3 Hiroshima atomic bombs. Now, before you panic, understand that seismic energy and explosive energy are not the same thing. An atomic bomb releases its energy in a fraction of a second in one location, vaporizing everything nearby. These earthquakes release their energy slowly across thousands of miles through the friction of tectonic plates sliding past each other. It's the difference between a punch and sustained pressure. But here's what matters. That energy had to come from somewhere. And the way it came out, all at once, in moderate doses, scattered across unrelated fault systems, is not how Earth usually works. Earth is chaotic. Faults are loaded by the slow grind of tectonic plates, building stress over decades or centuries until something snaps. When it snaps, it's usually big and local. You get your magnitude 7.5 in California, your 8.9 in Japan. The release is concentrated. The pattern is predictable. But on January 26th, the release was global. It was as if the planet decided to exhale all at once instead of holding its breath until something catastrophic gave way. And here's the part that should make you uncomfortable. This specific pattern, multiple magnitude 5+ quakes without a single magnitude 6+, has only been recorded one other time in modern seismic history, January 24th, 2021. 5 years ago, almost to the day. You starting to see why this matters? Now let's talk about what happened 16 days before January 26th, because that's where things get really interesting. January 10th, 2026. The sun unleashed a solar radiation storm so intense that it briefly registered as an S3 event on the NOAA space weather scale. For those of you who don't speak space weather, that scale goes from S1 to S5. S5 means satellites die and astronauts hide, and S3 is serious. It means high-energy protons are slamming into Earth's magnetic field at speeds that make a bullet look lazy. The proton flux, the measure of how many particles are hitting a given area, peaked at over 10,000 particle flux units. That's not the highest ever recorded, but it's high enough to disrupt satellites, interfere with polar aviation, and generally remind us that space is not as empty as it looks. Here's where it gets weird. We're in solar cycle 25. Solar cycles last about 11 years, and they follow a predictable rise and fall. We hit solar maximum, the peak of activity, around 2024. By early 2026, the sun should be calming down. Flares should be getting less frequent. Coronal mass ejections should be weakening. Radiation storms should be tapering off. That's the pattern. That's what the models predict. But January 10th said otherwise. Instead of weakening, the sun delivered one of the strongest radiation storms in decades, comparable to events seen during solar maximum, not on the declining phase. So what exactly is a solar radiation storm? It's not the same as a geomagnetic storm, though the two often get confused. A geomagnetic storm happens when a coronal mass ejection, a massive cloud of charged particles, slams into Earth's magnetosphere and causes the magnetic field to wobble and compress. That's what gives you auroras and power grid issues. A radiation storm, on the other hand, is when high-energy protons, accelerated by solar flares, come racing toward Earth at near the speed of light. They don't interact much with the magnetosphere. They just punch straight through, ionizing the upper atmosphere and creating secondary radiation cascades. It's like the difference between being hit by a wave and being hit by a hail of bullets. The January 10th storm lasted several hours. Proton flux spiked. Polar flight routes were diverted. Satellite operators put their systems into safe mode, and then it passed. The sun quieted down. The radiation levels dropped. Life went on. But 16 days later, the Earth shook. 15 times, everywhere. Now, here's where we need to tread carefully. The idea that solar activity can influence seismic activity is not new. It's also not accepted. It's one of those fringe hypotheses that pops up every few years, usually after a major solar storm coincides with a major earthquake, and then gets dismissed because the statistical evidence is weak and the physical mechanism is unclear. Most seismologists will tell you there's no credible link. Solar storms affect the upper atmosphere and the magnetosphere. Earthquakes happen in the crust, dozens of miles below. The two systems don't talk to each other. End of story. Except the story doesn't quite end there, because there are correlations. Weak correlations? Yes, but correlations nonetheless. Studies have found slight upticks in seismic activity during periods of high solar activity. Not huge upticks, not enough to predict earthquakes, but enough to make you wonder if something subtle is going on. And then there's the lag. If solar storms do influence seismicity, they don't do it immediately. The effect, if it exists, seems to show up days to weeks later. Some researchers have proposed a 16-day lag as a possible signature. Why 16 days? Nobody knows. It might have to do with how energy propagates through the magnetosphere and ionosphere. It might have to do with how atmospheric changes translate into pressure shifts on the crust. It might be noise, but it keeps showing up. Let's look at history. The Carrington event of 1859, the largest solar storm on record, coincided with unusual seismic activity in the weeks that followed. The Halloween storms of 2003, another major solar outburst, were followed by a magnitude 8.3 quake in Japan. In 2004, after another solar maximum, the magnitude 9.1 Sumatra quake struck. Are these coincidences? Probably. Earthquakes happen all the time. Solar storms happen all the time. Sometimes they overlap. But the fact that researchers keep coming back to this question suggests that the intuition, the nagging sense that there might be a connection, refuses to die. And here's the thing, we're not talking about the sun causing earthquakes. We're not saying solar flares crack tectonic plates. The energy involved is nowhere near enough for that. What we're talking about is triggering. The idea that faults already loaded with stress, already on the verge of failure, might be nudged over the edge by subtle changes in the environment, changes in electromagnetic fields, changes in atmospheric pressure, changes in ionospheric conductivity, tiny perturbations that wouldn't matter if the system weren't already primed to go. So the question becomes, can energy from a solar storm propagate down through the atmosphere and into the crust? Can it change conditions enough to act as a trigger? And if it can, would it leave a signature? Would it look like 15 scattered magnitude 5 quakes instead of one big rupture? We don't know. But we're about to walk through the chain of events that would have to occur for it to work. And each link in that chain is individually plausible. The controversy is whether they connect. If you want to understand how something happening 93 million miles away could possibly affect what happens 30 miles beneath your feet, you need to think in layers. Earth is not a billiard ball. It's a nested system of shells, each with its own properties, each interacting with the layers above and below. And when something disturbs the top layer, those disturbances can theoretically propagate downward, not as a direct force, but as a cascade of secondary effects. Let me walk you through what that cascade might look like. Step 1. The sun ejects high-energy protons. These particles race toward Earth at speeds approaching the speed of light. When they hit our magnetosphere, that invisible magnetic shield surrounding the planet, they don't just bounce off. They interact. They compress the magnetosphere on the sunward side, stretching it out into a long tail on the night side. This compression is not gentle, it's a squeeze. And when you squeeze a magnetic field, you induce electric currents. These currents flow through the magnetosphere and down into the ionosphere, the layer of the atmosphere about 50 to 600 miles up, where solar radiation ionizes gas molecules, creating charged particles. Step 2. The ionosphere becomes overconductive. Normally, the ionosphere has a baseline level of conductivity. It's a decent conductor, but not a great one. During a solar radiation storm, though, the proton flux ionizes more molecules, increasing the number of free electrons. More electrons mean higher conductivity, and higher conductivity means electric currents can flow more easily. This matters because the ionosphere is part of a global electrical system. There's a voltage difference between the ionosphere and Earth's surface, maintained by thunderstorms and other atmospheric processes. When the ionosphere's conductivity changes, the distribution of electric currents in this system also changes. Step 3. Atmospheric effects. Now, this is where it gets speculative, but stay with me. There's evidence that solar storms can influence atmospheric circulation patterns, particularly in the polar regions. During the January 10th storm, the polar vortex, that swirling mass of cold air over the Arctic, showed signs of instability. Polar vortex disruptions are not uncommon, but the timing is interesting. When the vortex weakens or splits, it redistributes atmospheric mass. Cold air that was concentrated over the pole spills southward. Warmer air pushes northward. The pressure gradients shift, and when pressure gradients shift, so does the weight of the atmosphere pressing down on Earth's surface. Step 4. Atmospheric loading. This is a real, measurable effect. The atmosphere has mass, about 5 quadrillion kilograms of it, and that mass is not evenly distributed. High-pressure systems weigh more. Low-pressure systems weigh less. When a high-pressure system parks itself over a fault zone, it exerts a downward force on the crust. When a low-pressure system moves in, it reduces that force. These changes in pressure are small, a few millibars at most, but they translate into stress changes on faults. Studies have shown that atmospheric pressure variations can influence the timing of earthquakes, particularly for faults that are already close to failure. It's not that pressure causes the quake. It's that pressure changes the clock. It nudges a fault that was going to rupture next week into rupturing today. Step 5. The lithosphere responds. Now, here's where most seismologists get off the train. The argument is that atmospheric pressure changes are too small to matter. The tectonic forces building stress on faults are enormous, measured in megapascals. Atmospheric pressure changes are measured in kilopascals. It's like trying to tip over a truck by blowing on it. And yet, in complex systems, small perturbations can have large effects if the system is in a critical state. Think of an avalanche. You don't need a boulder to start an avalanche. A single snowflake landing on an unstable slope can do it. The energy for the avalanche was already there, stored in the snowpack. The snowflake just provided the final trigger. So the hypothesis, the chain of events, goes like this. Solar radiation storm hits. Magnetosphere compresses. Ionosphere becomes more conductive. Atmospheric circulation shifts. Pressure redistributes. Stress on faults changes. Faults that were already on the edge of failure slip. Not all faults, just the ones that were primed. And if the atmospheric redistribution happens globally, if the pressure changes are widespread, then you might see multiple faults slipping at the same time, not because they're connected mechanically, but because they're all responding to the same environmental trigger. This is not a mainstream idea. Most geophysicists would call it highly speculative at best and pseudoscience at worst. The problem is that each individual link in the chain is studied by a different field. Solar physicists study the sun. Space physicists study the magnetosphere. Atmospheric scientists study weather. Seismologists study earthquakes, and very few people are looking at how all these systems connect. Each field tends to stop at its boundary and assume that what's happening in the next layer down is someone else's problem. But Earth doesn't work that way. Earth is one system, and systems talk to each other. So the question is not whether this chain is proven. It's not. The question is whether it's plausible, and the answer is uncomfortably yes. Each link is individually plausible. The controversy is whether the chain can propagate all the way from the sun to the crust without losing signal, whether the effects are strong enough to matter, whether the timing works out, and whether we would even know if it did, given how rarely we measure all these variables at once. But wait. There's one more coincidence we haven't talked about yet. One more piece of timing that makes the whole thing feel less like a cascade of physical processes and more like the universe is trying to tell us something. Because on January 26th, 2026, something else happened. Something that occurs once every 165 years. Neptune entered Aries. Let me be very clear about something before we go any further. Astrology does not cause earthquakes. The gravitational pull of Neptune, a planet 30 times farther from the sun than Earth, is negligible. Its electromagnetic influence is zero. There is no known physical mechanism by which the position of Neptune in the sky could exert any force on tectonic plates. None. And yet, here we are talking about it. Why? Because the timing is impossible to ignore. Neptune entered Aries on January 26, 2026, the exact same day as the global seismic event. Neptune takes about 165 years to orbit the sun, which means it spends roughly 14 years in each zodiac sign. The last time Neptune entered Aries was 1861. Before that, 1696. These are not random dates. Astrologers have been tracking this event for decades. They flagged January 26th years in advance, calling it a once-in-a-lifetime planetary shift, the beginning of a new era. And then the Earth shook 15 times, everywhere. Now let's talk about what happened in 1861. The American Civil War started. Italy unified. Serfdom was abolished in Russia. It was a year of massive upheaval, the kind of year where the old order crumbled and something new, chaotic, and transformative emerged. Astrologers point to this and say, see, Neptune in Aries brings disruption. It breaks patterns. It forces change. Skeptics point to this and say, correlation is not causation. Major events happen every year. If you look for patterns, you'll find them. Both sides are right. Both sides are also missing the point. The point is not whether astrology is real. The point is that humans have been tracking celestial patterns and correlating them with earthly events for thousands of years. And sometimes those correlations are uncanny. Not because the planets are pulling strings, but because the patterns we see in the sky reflect patterns we see in human behavior, in natural cycles, in the rhythm of change itself. Carl Jung called this synchronicity. The idea that events can be meaningfully related without being causally related. That sometimes the universe just lines things up in a way that feels intentional, even if it's not. So what do we do with the fact that Neptune entered Aries on the exact day of a once-in-a-decade seismic pattern? We acknowledge it. We sit with the discomfort. We resist the urge to either dismiss it as meaningless or elevate it to proof of cosmic design. Because the truth is, we don't know. We don't know if it's coincidence. We don't know if there's some some deeper pattern we're not seeing. We don't know if the timing is trying to tell us something, or if we're just pattern-seeking primates desperate to find meaning in chaos. Here's what we do know. Humans are really good at finding patterns. It's how we survived as a species. See a rustle in the grass twice. Assume it's a predator. Live to see another day. The cost of a false positive is low. The cost of a false negative is death. So our brains are wired to see connections, even when they're not there. This is why we see faces in clouds. Why we think our lucky socks help us win games. Why we read horoscopes and nod along, even when they're vague enough to apply to anyone. We're pattern matching machines. And most of the time, we're matching noise. But sometimes, the pattern is real. Sometimes the rustle in the grass really is a predator. And the hard part is figuring out which is which. Science is supposed to help us do that. Science is supposed to separate signal from noise, causation from correlation, reality from illusion. But science is also a human endeavor, and humans are bad at dealing with uncertainty. We want clean answers. We want mechanisms. We want to know why. And when we can't find a mechanism, we tend to dismiss the pattern as noise, even if the pattern keeps showing up. So maybe the Neptune thing is noise. Maybe it's just a coincidence that this planetary alignment happened on the same day as a rare seismic event that followed a rare solar event 16 days earlier. Maybe the universe is just indifferent, and we're reading tea leaves, or maybe, just maybe, there's a layer of order we're not seeing yet. Not because the planets are gods, not because astrology is physics, but because we live in a universe where cycles nest inside cycles, where rhythms on one scale can resonate with rhythms on another scale, where timing, even if we don't understand the mechanism, still matters. And here's the uncomfortable part. If you ask most seismologists if they believe in astrology, they'll say no. Absolutely not. It's superstition. It's anti-science. But if you ask them if they believe in tidal forces, if they believe that the gravitational pull of the moon and sun can influence earthquake timing, they'll say yes. Maybe. The evidence is mixed, but it's plausible. So where's the line? When does gravitational influence become astrology? When does pattern recognition become superstition? These are not easy questions, and they don't have clean answers. What we're left with is discomfort. The discomfort of not knowing. The discomfort of seeing a pattern that feels significant but having no way to prove it. The discomfort of standing at the edge of what science can explain and staring into the territory of what it can't. And maybe that's okay. Maybe discomfort is the appropriate response. Because the alternative is certainty. And certainty, when it's not warranted, is just another form of delusion. So let's move forward with that discomfort. Let's stop treating January 26th as an isolated event and start treating it as a data point, one piece of a larger puzzle. Because if there's a mechanism connecting solar storms to seismic activity, if there's a reason why Earth released energy the way it did, we're going to need to dig deeper. We're going to need to look at the systems we don't usually look at. The electrical systems, the atmospheric systems, the parts of Earth's infrastructure we take for granted. And that's where things get even stranger. If you were going to design a system to distribute energy from the upper atmosphere down to the surface of Earth, you couldn't do much better than the global electric circuit. It's elegant, it's planetary scale, and most people have never heard of it. Here's how it works. At any given moment, there are about 2,000 thunderstorms happening somewhere on Earth. Each thunderstorm acts like a battery, separating positive and negative charges. Lightning strikes carry negative charge from the clouds to the ground, but in between strikes, a much slower, continuous current flows upward from the ground to the ionosphere, carrying positive charge. This creates a voltage difference between Earth's surface, which is negatively charged, and the ionosphere, which is positively charged. The voltage difference is about 300,000 volts. That sounds like a lot, but it's spread over the entire planet. So the electric field at ground level is only about 100 volts per meter. You don't feel it because you're conductive. The current flows through you harmlessly. But the circuit doesn't stop there. In regions without thunderstorms, current flows back down from the ionosphere to the surface, completing the loop. So you have a global system where charge is constantly being pumped up by thunderstorms and flowing back down in fair weather regions. It's a continuous circulation of electrical energy driven by atmospheric convection and maintained by solar radiation ionizing the upper atmosphere. And it's stable. The global electric circuit has been running for as long as we've had an atmosphere capable of supporting it. Now here's where solar storms come in. When a solar storm increases the ionospheric conductivity, it changes the resistance of the circuit. Lower resistance means current can flow more easily. More current flowing means a stronger electric field at the surface. And a stronger electric field means more charge accumulating on conductive surfaces, including the ground, including rocks, including fault zones. The effect is small, maybe a few percent change in the local electric field. But remember, we're not looking for massive effects. We're looking for triggers, small perturbations that can nudge a system already on the edge. There's another piece to this. When the ionosphere becomes more conductive during a solar storm, it can change the current flow paths in the global circuit. Normally, current flows fairly uniformly around the planet. But if conductivity increases more in some regions than others, say in the polar regions where solar radiation hits most directly, then current can concentrate. It can channel along specific paths, following gradients in conductivity. And if those paths happen to cross fault zones that are already under stress, you get a localized enhancement of the electric field, exactly where you don't want it. This is speculative. Nobody has measured this directly, but the physics supports it. The global electric circuit is real. Solar storms do change ionospheric conductivity. Those changes do alter current flow. The question is magnitude. Are the changes large enough to matter? Could a few percent increase in electric field be enough to alter fault behavior? In most cases, probably not. But if a fault is already on the verge of failure, if it's in a critical state where the smallest perturbation could tip it over, then maybe, just maybe. And here's why this matters for January 26th. If the January 10th solar storm increased ionospheric conductivity globally, and if that increase persisted or had delayed effects through atmospheric coupling, then by January 26th, the global electric circuit might have been operating in a slightly altered state. Not dramatically different, just enough off baseline to create conditions where multiple faults, all independently close to failure, might have slipped within the same time window. Not because they were connected mechanically, but because they were all responding to the same subtle shift in the electrical environment. This is not the kind of explanation you can test with a simple experiment. You can't put a fault in a lab and zap it with electricity and watch it rupture. Real faults are complex, heterogeneous, loaded over decades. What you can do is monitor. You can measure telluric currents during solar storms. You can track changes in the global electric circuit. You can look for correlations between ionospheric disturbances and seismic activity. And some researchers have done this. The results are mixed. Some studies find weak correlations. Some find nothing. None of it is conclusive. But the fact that the system exists, the fact that it's planetary scale and driven by solar activity, the fact that it creates electric fields in the crust, all of that is real. It's not pseudoscience. It's just understudied. Atmospheric scientists know about the global electric circuit, but they mostly care about its effects on weather and climate. Seismologists know about telluric currents, but they mostly treat them as noise in their instruments. Nobody's really looking at how the two systems interact. Nobody's asking whether changes in the circuit could influence fault behavior. And that's a gap in our understanding of how Earth works as a system. So when you ask, could a solar storm influence earthquakes? The answer is not a simple yes or no. The answer is, there are pathways, there are mechanisms, they're weak, they're indirect, they're poorly understood, but they exist. And in a complex system, weak pathways can matter. If the timing is right, if the conditions align, if the planet is already primed. And speaking of gaps in understanding, there's a big one we need to talk about. A monitoring gap. A place where we used to have eyes and ears, and now we're flying blind. It's called the radiation belts, and we have no idea what they're doing right now. In May 2024, something unexpected happened. A solar storm hit Earth. And instead of just creating the usual disturbances in the magnetosphere, it created a new radiation belt, a temporary structure, a ring of high-energy protons trapped in Earth's magnetic field that shouldn't have been there. NASA scientists were surprised. They published papers. They called it an unprecedented event. And then the instruments went dark. Let me explain. Earth has two main radiation belts, called the Van Allen belts, named after the physicist who discovered them in 1958. The inner belt sits about 600 to 6,000 miles above the surface. It's mostly protons. The outer belt sits about 13,000 to 37,000 miles up. It's mostly electrons. These belts are dangerous. They're zones of intense radiation that can fry satellites, damage spacecraft electronics, and pose a serious risk to astronauts. We've been monitoring them for decades because understanding their behavior is critical for space operations. But here's the problem. The two missions that were actively monitoring the Van Allen belts, the Van Allen probes, were decommissioned in 2019. They ran out of fuel. They were shut down. Since then, our monitoring has been spotty. We have some data from other satellites, but nothing like the comprehensive, real-time coverage we used to have. And in 2024, NASA launched a new mission called SIR-B, the Cusp Region Imaging and Radiation Belt Experiment. It was supposed to fill the gap. It was supposed to give us continuous monitoring of the radiation environment, but SIR-B has been silent. No public data releases, no updates, radio silence. So when the May 2024 storm created that unexpected radiation belt, we caught it because there were just enough instruments still operational to notice. But since then, we don't know. We don't know if the belt persisted. We don't know if it intensified. We don't know what the radiation environment looked like during the January 10th storm. We don't know what it looked like on January 26th. We're flying blind. This is not a small problem. Radiation belts are not static. They change in response to solar activity. During major storms, they can intensify dramatically, they can expand, they can shift in shape, and when they do, they can affect not just satellites, but also the upper atmosphere. High-energy particles colliding with atmospheric molecules create secondary cascades of ionization. They alter conductivity, they heat the atmosphere, they change the chemistry. All of these effects can, in theory, propagate downward. But without real-time monitoring, we have no idea what's actually happening up there. Now, I'm not suggesting a conspiracy. I don't think NASA is hiding data. I think the more mundane explanation is probably correct. SIR-B might be experiencing technical issues. The data might not be processed yet. The mission might be delayed. These things happen, but the consequence is the same. We're in a period where we need to understand the radiation environment more than ever, and we can't. We're making decisions about satellite operations, aviation routes, astronaut safety, based on models and assumptions, not real-time data. And models are only as good as the data they're trained on. Here's why this matters for January 26th. If the January 10th storm did something unusual to the radiation belts, if it created structures or intensified existing ones that could have prolonged the ionospheric disturbances, it could have kept conductivity elevated for days or weeks, it could have created conditions where the global electric circuit was operating in an altered state well into late January. But we don't know. We can't check. The instruments aren't there. This is what unknown unknowns look like. We know we don't know what's happening in the radiation belts, but we don't know what the consequences of not knowing are. We don't know if the gaps in our knowledge are hiding something important, or if they're just gaps. And that uncertainty is uncomfortable. It means we're operating on faith. Faith that the models are good enough. Faith that the old data still applies. Faith that nothing has changed in ways we can't predict. And maybe that faith is justified. Maybe the radiation belts are behaving exactly as expected. Maybe the January 10th storm was intense but unremarkable. Maybe we're worrying about nothing. But here's the thing. Every time we think we understand space weather, it surprises us. Every time we think we've seen the worst the sun can throw at us, it does something new. The May 2024 belt was unexpected. The January 10th storm was stronger than it should have been. And now we're in a position where we can't see what's happening above us during a period of unusual activity below us. That's not a comfortable position to be in. And it's not just about space weather, it's about Earth's defenses. Because while we've been focused on what's happening in space, something fundamental has been changing here at home. Earth's magnetic field, the shield that protects us from all of this, is weakening faster than it should be. You probably don't think about Earth's magnetic field very often. Most people don't. It's invisible. It doesn't affect your daily life in any obvious way. Your phone works. Your car starts. The sun rises. But the magnetic field is there, constantly, wrapping around the planet like a protective bubble, deflecting solar wind, trapping radiation in the Van Allen belts, keeping the atmosphere from being stripped away. Without it, Earth would look like Mars, dead, sterile, uninhabitable, and it's changing. faster than it should be. Earth's magnetic field is generated by the motion of molten iron in the outer core, about 1/800 miles down. That motion creates electric currents, and those currents generate a magnetic field. It's a self-sustaining dynamo, powered by the heat escaping from the core. The field has existed for at least 3.4 billion years, and it's been relatively stable for most of that time. But stable doesn't mean static. The field wanders. The magnetic poles drift. The strength fluctuates, and every few 100,000 years, it flips. North becomes south. South becomes north. This is called a geomagnetic reversal, and it's a normal part of Earth's behavior. The problem is, we might be in the early stages of one right now. The current magnetic field is about 10% weaker than it was 200 years ago. That might not sound like much, but the rate of weakening is accelerating, and the field isn't weakening uniformly. There's a region over the South Atlantic stretching from South America to Southern Africa, where the field is particularly weak. It's called the South Atlantic anomaly, and it's growing. Satellites passing through this region experience higher radiation doses. Spacecraft electronics glitch. The Hubble Space Telescope has to shut down some of its instruments when it flies over the anomaly to avoid damage. The European Space Agency has been tracking the anomaly with a constellation of satellites called SWARM. The data shows that the anomaly is not just weakening, it's also splitting. A second region of weak field is forming over Southern Africa, and the two are starting to merge. This kind of behavior, multiple weak spots appearing and interacting, is consistent with what models predict might happen during the early stages of a reversal. But here's the thing, reversals don't happen overnight. They take thousands of years, and during that time, the field doesn't disappear. It just becomes more chaotic. Instead of a simple dipole, north and south poles, you get multiple poles. Shifting orientations, regions of very weak and very strong fields scattered across the planet. Now, why does this matter for space weather? Because a weaker magnetic field means less protection. Solar storms that would have been deflected or absorbed by a stronger field can now penetrate deeper into the atmosphere. Radiation that would have been trapped in the belts can now reach lower altitudes. The ionosphere becomes more vulnerable. The atmosphere becomes more conductive. And if the hypothesis about solar storms influencing seismic activity has any validity, a weaker magnetic field would make Earth more sensitive to those influences. It would lower the threshold. It would make rare events more common. This is not speculative. The field is weakening. The anomaly is growing. These are observed facts. What's speculative is what the consequences are. How much weaker does the field have to get before we see significant effects? How much more vulnerable is Earth now compared to 100 years ago? How much more vulnerable will it be in 50 years? We don't know. The models are uncertain. The historical data is limited. But the trend is clear. We're heading into a period of increased vulnerability. And it's not just satellites and astronauts who need to worry. Aviation is affected too. High-altitude polar routes are already experiencing increased radiation doses during solar storms. Pilots and flight attendants accumulate more exposure. Regulatory agencies are starting to set limits. Some flights are being rerouted. And as the field continues to weaken, these problems will get worse. The question is how fast, and whether we're prepared. But preparation requires acknowledging the risk. It requires admitting that the assumptions we've been operating under, the idea that the magnetic field is stable and we can predict space weather based on historical patterns, might not hold anymore. It requires updating our models, our infrastructure, our policies. And that's slow. Institutions are slow. They react to crises, not trends. And by the time the crisis is obvious, it's often too late to prepare properly. So here we are. The field is changing. The anomaly is growing. We're more vulnerable than we used to be. And January 10th, 2026 was a test, a stress test. The storm was strong, but not catastrophic. It disrupted satellites. It forced flight reroutes. It created that mysterious radiation belt. But it didn't bring down the grid. It didn't cause mass casualties. It was a warning shot, a reminder that space weather is real, that it can hurt us, that we need to take it seriously. The question is, will we? Or will we do what humans always do, file it away, assume it won't happen again, and go back to our daily lives? History suggests the latter. We're not good at preparing for low-probability, high-consequence events. We're reactive, not proactive. We wait for the disaster and then scramble to respond. That strategy works for tornadoes and hurricanes, events that happen frequently enough that we've developed response capabilities. It doesn't work for events that happen once a century or less, because by the time we experience it, it's too late to prepare. And if a Carrington-level event, the kind of solar superstorm that happened in 1859, hit us now, with the field as weak as it is, the consequences could be catastrophic. Power grids down, satellites lost, communication systems fried, not for hours or days, for weeks or months, and we're not ready, not even close. So where does this leave us? We have a planet that just did something it's only done once before in recorded history, a synchronized release of seismic energy across multiple continents. No main event, no aftershock sequence, just 15 moderate quakes firing off like a coordinated pulse. We have a solar storm that hit 16 days earlier, stronger than it should have been, creating radiation belt structures we didn't expect, altering the ionosphere in ways we can't fully monitor because our instruments are offline. We have a weakening magnetic field, a growing anomaly, a planet becoming more vulnerable to space weather with each passing year. We have a global electric circuit that connects the sun to the ground through invisible pathways of current and charge, a system that most scientists don't even think about because it falls between disciplines. And we have a planetary alignment that astrologers flagged years in advance, a once-in-165 years event that happened on the exact same day as the seismic pattern. Coincidence? Maybe. Pattern? Possibly. Warning? That's the question nobody wants to ask out loud. Because if January 26th was a warning, what was it warning us about? Let me offer a reframing. What if January 26th wasn't a disaster? What if it was calibration? Think about it. If you're a system under stress, if you're a planet with tectonic plates grinding, faults loading, pressure building, you have two options. You can let that stress concentrate until something catastrophic breaks, or you can release it gradually, in smaller increments, distributed across multiple locations. The first option gives you magnitude 8 quakes, tsunamis, mass casualties. The second option gives you 15 magnitude 5s, rattled nerves, cracked walls, but no catastrophe. From a human perspective, we prefer the second option. It's less destructive. But from a physics perspective, it's actually more interesting. Because it requires coordination, it requires that multiple faults in multiple locations all release at roughly the same time. And in a chaotic system like Earth's crust, that shouldn't happen, unless something is synchronizing them. Now, I'm not suggesting Earth is conscious. I'm not suggesting it makes decisions. But complex systems do self-organize. They do find equilibrium states. They do regulate, not through intention, but through feedback. When pressure builds in one place, it redistributes. When stress concentrates, it finds release valves. And if the system is being perturbed by external forces, if solar activity is nudging faults that are close to failure, then maybe, just maybe, the result is a distributed release. A global exhale, a pressure adjustment that prevents a localized catastrophe. This is the low distribution hypothesis, the idea that Earth, under certain conditions, can release tectonic stress in a coordinated way instead of letting it accumulate until a major rupture occurs. It's not proven, it's not even widely discussed, but it fits the pattern. It explains why you'd see multiple moderate quakes instead of one large one. It explains why they'd be scattered instead of clustered. It explains why the timing might correlate with solar activity. If solar activity acts as a trigger, and it raises a possibility that most seismologists would find uncomfortable, that Earth might have mechanisms for self-regulation that we haven't discovered yet. That the planet might be more sophisticated in how it handles stress than we've given it credit for. But if this hypothesis has any validity, it raises a disturbing question: what happens next? If January 26th was a calibration, if Earth was adjusting, then what was it adjusting to? What's coming? Was this a one-time release, or the first in a series? Was it Earth clearing accumulated stress, or preparing for something larger? We don't know. But the fact that we have to ask these questions tells you how far outside our normal framework we've wandered. We're used to thinking about earthquakes as isolated events, driven by local tectonics. We're not used to thinking about them as part of a planetary scale response to external forcing. But maybe we need to start, because on February 20th, 2026, there's another astronomical event. Saturn and Neptune will be in exact conjunction, aligning in the sky as seen from Earth. This doesn't happen often. The last Saturn-Neptune conjunction was in 1989. The next one after this year will be in 2047. Astrologers have flagged this date as significant. a culmination of the Neptune in Aries energy, a moment of structural reckoning. I'm not endorsing astrology, I'm just noting the timing. Because if the pattern holds, if rare astronomical configurations correlate with rare terrestrial events, then February 20th is worth watching. Not because the planets are causing anything, but because rare alignments might serve as markers, as cosmic timestamps that correlate with periods when Earth's own internal rhythms are also reaching critical points. Correlation without causation, but correlation that still matters. And it's not just February. It's the whole year. We're in a period of heightened solar activity. Solar cycle 25 is proving more active than forecasters predicted. The magnetic field is weakening. The South Atlantic anomaly is growing and potentially splitting. The radiation environment is uncertain because our monitoring satellites are offline or silent. The atmospheric circulation is unstable. Polar vortex disruptions, unusual jet stream behavior. The tectonic plates are still grinding, accumulating stress that will eventually have to be released. All the conditions that might have contributed to January 26th are still present, maybe even intensifying. So if you're asking whether we should expect more unusual seismic activity, more storms, more surprises, the answer is probably yes. Not because I'm predicting it, but because the background conditions favor it. We're in a high variance period, a time when the unlikely becomes more likely, when statistical outliers cluster, when the rules we thought were solid start to bend. So what should you watch for? 3 things. First, solar activity. If another major storm hits, particularly one comparable to or larger than January 10th, pay attention to what happens in the days and weeks afterward. See if seismic activity upticks. See if the pattern repeats. A single correlation could be coincidence. 2 correlations make you curious. 3 correlations make you start looking for mechanisms. We're at 2 now. 1 more, and the scientific community will have to take this seriously, whether they want to or not. Second, magnetic field changes. Watch for updates on the South Atlantic anomaly. The European Space Agency's SWARM mission is tracking it continuously. If it continues to grow or split, if the field continues to weaken at its current rate or faster, that's a sign that we're becoming more vulnerable to space weather effects. It means solar storms that would have been minor irritants 50 years ago could now have significant impacts. It means our infrastructure assumptions are outdated. It means we're operating in a regime where the historical data no longer applies because the boundary conditions have changed. Third, AI-driven predictions. If models start flagging increased probabilities of coordinated seismic events, don't dismiss them just because the mechanism is unclear. The models might be seeing something we're not. They might be picking up on subtle patterns in atmospheric pressure, in electromagnetic field fluctuations, in ionospheric conductivity that correlate with fault behavior. Remember, AI doesn't need to understand causation to identify correlation, and in complex systems, correlation can be predictive even when we don't understand why. It's not ideal. We'd prefer to understand the mechanism. But if the choice is between predictions we don't understand and no predictions at all, I'll take the predictions. But here's the thing. Watching is not the same as worrying. I'm not trying to scare you. I'm trying to inform you. The universe is not out to get us. Earth is not angry. The planets are not conspiring. What's happening is natural. It's just complex. And complexity looks like chaos until you see the pattern. And even when you see the pattern, you don't always understand it. That's okay. That's normal. That's how discovery works. First you notice something strange, then you look for patterns, then you try to understand the patterns, then you test your understanding. And if you're lucky, you eventually figure out what's actually going on. But that process takes time, years, decades, sometimes centuries. We're at step 2. We've noticed something strange. We're looking for patterns. Understanding will come later, maybe. So the question that refuses to go away, the question of what happened on January 26th, might not have a simple answer. It might not even have an answer at all. It might just be a moment when multiple systems, operating on their own timescales, happen to converge. A coincidence? A fluke? A statistical anomaly that we'll never see again. The universe is full of those. Random events that look meaningful but aren't. Our brains are wired to see patterns, even in noise. Maybe this is noise. Or it might be something else. It might be the first clear signal that Earth's behavior is shifting. that the systems we thought were separate are actually coupled, that the planet is responding to its environment in ways we haven't fully appreciated, that we're entering a period where the old assumptions don't hold and the new rules haven't been written yet. A transition period, a threshold, the kind of moment that, in retrospect, historians of science will point to as the beginning of a paradigm shift, when the data stopped fitting the models, and we had to start asking new questions. And maybe that's okay. Maybe we don't need certainty. Maybe what we need is awareness. Awareness that Earth is dynamic, that it surprises us, that it doesn't owe us predictability, and awareness that we're part of this system, not separate from it. When the Earth shakes, it's not attacking us. It's just being Earth, doing what it's always done, adjusting, releasing, breathing. We live on a geologically active planet. We always have. The only difference now is that we have instruments sensitive enough to see patterns we couldn't see before. And knowledge brings responsibility. The responsibility to look honestly at what the data is telling us, even when it's uncomfortable, even when it challenges our assumptions, even when we don't have all the answers yet. The Earth didn't scream on January 26th. It pulsed 15 times, everywhere. And whether that pulse was random or coordinated, chaotic or calibrated, is a question we'll be asking for years to come. But in the meantime, the planet keeps turning. The sun keeps flaring. The magnetic field keeps shifting. The faults keep loading. And somewhere, deep in the crust, the next stress point is building. Slowly, quietly, waiting for the moment when it too will release. And when it does, we'll be watching. We'll be measuring. We'll be asking the same questions all over again. Was it random? Was it triggered? Was it part of a pattern? And maybe eventually we'll get an answer. Or maybe we'll just get more questions. Because that's how science works. One observation at a time. One pattern at a time. One pulse at a time. The process is slow. It's frustrating. It requires patience and humility and a willingness to be wrong. But it's also the only process we have that reliably moves us toward truth. Not quickly, not cleanly, but inevitably. The Earth is speaking. The question is whether anyone is listening. And if they are, whether they're willing to hear what it's saying. Because sometimes the message isn't what we want to hear. Sometimes it's that we know less than we thought, that our models are incomplete, that the universe is stranger and more connected than our textbooks suggest. But that's not a reason to stop listening. It's a reason to listen harder. Drop a comment below telling me where you're watching from, what time it is there right now, and whether you think January 26th was random chance or something we're not being told. And if this video made you question reality the way it's shaken mine, hit that like button and subscribe, because this story isn't over. February 20th is coming, the solar cycle isn't finished, and Earth is still speaking.